here. So most basic example would be a monoid as a set. So a monoid is a set equipped with this multiplication map here, and it has to satisfy a certain associativity assumption. And it also has a unit map, which is a map from the singleton set to M, and it satisfies unitality. And another variation on this idea is this notion of an algebra. So an algebra is a vector space, and it's equipped again with the multiplication map. But this time, instead of doing a product, we do the tensor product instead. And it still has to satisfy the same associativity assumptions. And again, it has to satisfy this unitality assumption here. Okay, so what are we using when we make these definitions? So the first fact we're using is that there's some sort of operation. In the set case, it was Cartesian product. In the vector space case, it was tensor product. But in both cases, it's some operation that takes two sets, x and y, and yields a new object. We're also using the fact that there's another operation that basically joins the two morphisms in parallel. So a morphism here and a morphism here, and it gives you a new morphism from here to here. And we're also using the fact that there's a certain special object, which I'm just going to call 1 in the general case, such that 1 O dot with x is isomorphic to x, and also x O dot 1 is also isomorphic to x. So in the set case, that was a singleton set, and in the vector space case, that was the ground field K. Okay, and so categories with this structure are called monoidal categories. So we have lots of examples of monoidal categories. So again, we have sets, and the monoidal product is Cartesian product. Same with topological spaces. In pointed spaces, the standard monoidal product happens to be the smash product. In our modules, it's the tensor product. In endofunctors, it's composition, which explains the slogan that monads are monoids in the monoidal category of endofunctors. Okay, so what is a monoid in a monoidal category then? So again, it's the same definition. So if you have a monoidal category like this, a monoid is a particular object X equipped with certain morphisms. Again, we have this multiplication map. It has to satisfy associativity. And it also has to have this unit map here. So note that you may not necessarily have a notion of a unit element in an arbitrary monoidal category, but you always have at least morphisms of this form. So this allows you to still talk about units. Okay, and so now sort of the main topic for this talk is that operads are actually a type of monoid. So let me explain that a little bit. So recall a symmetric sequence is a sequence of objects xn for every natural number such that xn has an Sn action. So these can be anything, any sort of object. So an example of this would be, so little cubes form a symmetric sequence in topological spaces. So here we have a little n cube, or a little cube for every n, every arity n. And for each arity, these have an Sn action, which permutes the labels. And another example is a symmetric sequence in vector spaces, which would just be a collection of Vn's, such that Vn is a representation of each Sn. Okay, so I'm saying that these have some, this has a monoidal structure. So this is what the monoidal structure is. It's given by this complicated thing. So this is a little bit hard to digest, but the basic idea is that this product here encodes basically operatic composition data. So you should think of something in here as a picture looks something like this. But remember, like, there's no, like, these pictures, like, don't, this isn't a totally honest picture in the sense that these things are just SN modules. They only have an action. There's no such, we're not really plugging it into anything. So this is the basic idea, but in reality, each element in here is just a collection of things. So something from N2, something from M1, something from N2 again, and then something from M3. And this thing is supposed to produce an SN module, right? Something with an SN action. But these things only have, this thing has an S2 action, this thing has an S1 action, and this thing has an S2 action. So in order to get what we want, we have to take these actions and actually induce upwards to SN. And that will give you an SN action.
Maybe it'd be good to say what induce means. Possibly people haven't seen that notation.
I didn't quite hear that. Induce?
Oh, I said like possibly some people haven't seen what induce up means.
Yeah.
So maybe it's good to say what that is.
Right, yeah. Okay, so maybe imagine these are little cubes or something, right? So S1 is a little cube with two circles, or a little cube with two cubes inside. N2 is a little cube with one cube inside, and N3 is a cube with two smaller cubes inside. Okay. And this thing is supposed to, this whole thing, this whole composition data thing here is supposed to have a SN action. So it's supposed to have an S5 action, but it simply, it just doesn't, right? There's no, like S5 doesn't act upon these things together. So the way to fix that is to I don't know quite how to explain this, but you're sort of formally I don't know quite how to explain this, but so these things have an S2 cross S1 cross S2 action. This tuple does. And so you take that and you sort of freely allow Sn to act upon it. So maybe the element in S5, maybe 1 and 2, or permute 1 and 2, that will act upon this tuple just fine. But the permutation that transposes 2 and 3, that won't quite work the way you'd expect to. So you sort of have to allow it to freely act upon it.
So maybe like if we're in sets or something, helpful to say, maybe I'll just, oh, I guess I'm requesting permission to annotate.
Yeah, go ahead. Approve.
Okay, yeah, so like in sets, this thing, you know, if we're in the category of sets, this thing would be like SN cross over, I'll just say S5. Yeah. S5 cross over S2 cross S1 cross S2 into.
Yeah, I might be doing something wrong because I can't see anything.
Oh, okay. I'm writing in blue. Can people see that? Maybe I'm the only one seeing that.
I can't see
I
it.
can. Yeah, me neither.
Oh, okay. I don't know why I need to request permission for something I can only see. Whatever. So, like in sets, this would be like you take the NIs and you cross it with a symmetric group, but you cross it over this product of symmetric groups that's acting on both. Like you can view SI1 cross ... SIK as a subgroup of SN, so it acts on SN, but it also acts on this product of NIs. So like in that case, that's a formula. Like if you're in rings, you can like tensor over the group ring of the symmetric. You can tensor the group ring of the symmetric group with this module, but tensor it over the group ring of the product of the symmetric groups. There's probably some general formula where you just say co-limit or something.
Yeah.
But just, for like this thing shows up a bunch in representation theory, but like in case people haven't seen it before, I just wanted to say something. Oh yeah.
Okay. Do I have to? Oh, I can just continue. Looks like I'm stuck on this page.
Let me try to exit annotating. This seems like a useless feature if only I can see it, but it prevents you from.
For some reason, I can see it now.
Oh, yeah, it just appeared for
Yeah, it
me.
disappeared.
Okay, is there like some X button you can click to kill it?
Oh, maybe. Did that do it?
Yeah, I don't see it anymore, so hopefully you can.
Yeah, okay.
You can move on.
No, I'm free. Yeah. Okay, yeah, so this product we just defined is actually a monoidal structure in the category of symmetric sequences. So what do the monoids in this category look like? Well, we sort of just established that we should think of things in here as basically composition data. And so this thing takes composition data and then outputs something in our original M. So composition data, collections of composition data for M becomes a single M. So that's just the same thing as an operad, right? So you might ask, how does this compare with the classical definition? Well, I could sort of imagine two reactions to this. So if you like monoidal categories, you might think this is sort of the superior definition. And if perhaps you don't like monoidal categories, this might seem like a useless reformulation of something you already know. And really both definitions have their advantages. So when you're doing sort of more algebraic things, the monoidal definition is just sort of more natural and more fluid when you're working in that setting. And the classical one, obviously it's served us just fine so far for what we've done. And it's also a little bit better when you're trying to it's a bit more, it's easier to modify. So the definition that I just gave for operads actually isn't the right definition if you're only interested in non-unital things. So if you're only interested in non-unital things, you actually want to only be able, you only want to plug in these things one at a time because you don't have a unit. So they're just two different definitions with two different sets of advantages. Okay. So that's the Monoidal definition for operad in the classical sense. So let's try to figure out what's going on here. So the first question I'm going to ask is there anything going on under the hood? Does this definition, should we just take this definition at face value, or is there something actually powering the definition? Is there something deeper going on? And the second question I'll ask is, can this be adapted to other operad-like structures? And do basically the same thing, but with different structures. Okay, and so there's sort of three things that I've learned from working on this project. And the first thing I've learned is that there's a notion of bimodules, which are defined as functors of this form here, such that this G here is something called a groupoid, and C is a monoidal category. And these are very natural when you're trying to do these sorts of monoid type things. And the second thing I've learned is that bimodules are often defined by the elements of another base bimodule. So bimodules that we see in nature are often constructed out of another bimodule. And the third lesson is that bimodules can have generators. So I'll tell you what that means in more detail later. So we'll first deal with the first lesson. So to do that, let's define this category S. So this bold S here. So in this category, we have countably many objects. We have 0, 1, 2, and 3. And there's an identity morphism from here to here, another identity morphism from here to here, and then there is S2 many morphisms from 2 to 2, and then S3 many morphisms from 3 to 3 and onward. So there's a whole group worth of morphisms here. And since we have a category, we have to define what composition means. And I'm going to take composition to just be group multiplication. So if I have my object 3 here, and I take this morphism, which is represented by a group element, and follow it up with another group element, I'm going to define the composition to just be group multiplication. So what's the point of this definition? So we'll ask ourselves, what is a functor from this special category S? So we can think of this functor as sort of an interpretation of the abstract structure S in the concrete setting of M. So each of these group elements becomes an actual map. And these maps have to be such that they satisfy the same, such that they're compatible with the group multiplication that we defined here. So they're an interpretation in that sense. And you notice that there's nothing really special about set here, right? We can replace set with anything we want. It could be topological spaces, vector spaces, R modules, whatever. And what's important here is that this is the exact same thing as an S module, right? So imagine maybe M is little cubes again. So to each element in S3, there is a endo function, a map from M3 to M3 again. So that one would correspond to sending little cubes here to its permuted version over here. Okay, so this is just kind of a fancy way of talking about symmetric sequences using this special category S. Okay, so now back to the first lesson here. So what was our slogan again? So our slogan was that bimodules defined as functors grow from here to here, where G is a groupoid and C is monoidal, are natural from the monoid point of view. So what's going on here? So first of all, what is a groupoid? So a groupoid is a category where all morphisms are isomorphisms. So if we go back here, a little further, everything here was an isomorphism. It's the same idea. And we think of things with a G action as functors from that groupoid to our chosen monoidal category. And so then functors of this form, we think of actions, we think of this functor as something with basically a two-sided action. On one side, we have a contravariant action. And on the other side, we have what I'm going to call a covariant action. So to make this a little bit more concrete, talk about categories. So categories happen to be a certain kind of bimodule. So how does this work exactly? So let's suppose we have any category. So no particular structure. And that category induces an iso-A bimodule. So when I say iso-A, I mean the groupoid of isomorphisms of A. Hopefully I'm not going too fast here. Okay. So how does this make a bimodule? So it gives it, so we take two objects here. So an object in iso-A, another object in iso-A. And those two things together are associated to a set. So the set of all morphisms between A and B. Okay? And so then where do the actions come from? Well, the actions come from the isomorphisms. So if you have an isomorphism like this, from A prime to A, this induces what I call the contravariant action. So you have something here, so maybe a morphism, and then that gets sent to something in here. So notice that it's being pulled back, so that we have A here originally, and it's being pulled back to A prime. And that is induced by precomposing it with this isomorphism. And in a similar vein, we have another isomorphism tau. This induces a covariant action by post-composition. So the important thing here is that it's not just an inert set. It's something with some action on it. Okay, and so let's talk about composition. So what is composition in the category? So composition, sorry about that. Composition is we take a morphism of this type and a morphism of this type, and our category structure tells us how to get a morphism of this type here. And since we're sort of thinking of a category as something with an action on it, we notice that there's a certain equivariance property with respect to this middle variable here. So if we have some morphism here, oops, that didn't do what I thought it would. I guess it's not totally necessary. So if you have some morphism here, from X to Y and another morphism here from Y to Z, we can compose these. But we can also take this morphism here and act upon it. So this is kind of made up notation, but the idea is that we can take this here and post-compose it with this sigma, and we can also act upon it here in the inverse way. And this sort of goes like this instead. And of course, composing these things is the exact same result as composing these things, right? Because the middle things are going to cancel out. So it's equivariant with respect to that isomorphism action. And this is a little bit technical, but this equivariance can be encoded as something called a coend. So if you've never seen this before, this is sort of like a tensor product, right? So the idea with a tensor product is that, you know, it doesn't matter if you act here or if you act here, right? It sees them as an equivalent thing. So we have this thing here, and that gets sent to a particular morphism here. And this coend encodes the fact that the composition doesn't care. It's being acted upon like this. Okay, and so that leads to the natural monoidal structure for these bimodules. So if we have two different bimodules, it could be whatever. There's a monoidal product given by this coend. And so that was maybe a lot, but the key takeaway is that this composition structure in a category can be encoded as a monoid structure, right? So if you have some category, there's some associated monoid structure. And that monoid structure is through these bimodules. So that's what's most important out of this. Okay, and so now on to our second lesson. So what was our slogan again? So our slogan was bimodules are often defined by elements of another base bimodule. So in order to make this totally precise, it would have to get into certain technical details, but really the most important thing is the following. So for operads, we drew these certain pictures, right? We had, you know, we had a picture like this. It was, you know, 2, 1, and 2, and then below it was 3, right? And we sort of thought of these things as being plugged into one another. That's what I mean by Tinker Toys, right? They're these little shapes that we can plug into each other. And the reason why that little cartoon picture makes sense is explained by thinking of these little Tinker Toys as elements in a certain base bimodule. And the combinatorics of these Tinker Toys comes from a monoid structure of the base bimodule. So let's see what's going on here. So first of all, what does elements mean? So if the bimodule is a set bimodule, so if it's from here to sets, it has what's called a category of elements. So here the objects are just what you think they are. They're just elements, and these run over A and B. And then what are the morphisms? Well, the morphisms are just given by the bimodule maps, right? So if you have some element X and it belongs to row AB, and then there's a map between row AB and row A prime, B prime, then there's a morphism between X and Y given by the image of X here. So so now an example of this. So let's define this new category fin for finite sets. So the objects will be sets, underline n. So these are all numbers between 1 and n, for any natural number n. And then the morphisms are just going to be set maps. So they're just going to be maps from 1 through n to 1 through m. And like we said before, any category structure induces a bimodule, a set bimodule to be particular. So what was this structure again? So it was, so rho fin from n to m is precisely the set of maps from n to m. Okay, so what do the elements of this thing actually look like? Here's a picture. So on the left, we have this element here. So these are maps from 5 to 3, right? We can visualize it as this picture here. So you have this map here, 1 goes to 1, 2 goes to 3, etc. And it sort of forms this graphical picture here. And on the other hand, we have this morphism here, which is represented by this graphical picture. And the idea is that this bimodule structure induces this action here that basically twists the upper part and the lower part. So here, this, this permutes 2 and 3. So 2 goes to 3, and it goes there. This one's a little bit weird because it's acting contravariantly. So it's sort of doing the opposite of what you think it should do, but it's also twisting these things together. So this top part twists to become this top part here. Okay. So these have a monoidal product, or these at least induce a monoidal product. So we should think of functors D from L rho to C as assigning each tinker toy, so each little shape is assigned an object. So in the operad case, we assigned to one shape a topological space, for instance. And what's really nice is that if you work hard enough, these things actually have a monoidal structure. It's a very natural one. So we're not quite done just yet, right? So our third lesson was that bimodules can be generated by a subbimodule. So what's an example of this? Well, in our case of finite sets, all of these things are generated by n to 1 maps, right? So if you have a picture like this, these break up into fibers, basically. So we look at this fiber here, we get this. We look at this fiber here, and we get that. And we look at this fiber here, and we get this. Okay. That's what I mean by generated. And to talk about this in bimodule language, we would want to say that rho fin is freely generated by nu fin, where nu fin is this kind of this bimodule here. So it's a very simple bimodule. So if m is 1, then it's a set of all maps from n to 1. And if it's anything else, it's empty. So it's very simple. And we want to say that rho fin is freely generated from this. So again, this seems pretty simple to do, but it's actually somewhat technical to make this work in a general setting. But it can be done. That's something I'm actually pretty happy about. So this leads us to considering things in this subbimodule. So instead of considering just general elements, we can consider the basic elements, the things that all the elements are generated from. So things like this. And by doing a little bit of work, we can show that these also have a Monoidal product. These particular functors here have a Monoidal product. And we can do that by adapting the one from before. Okay, so let's consider our example again. So you have our bimodule rho fin. And what is rho fin? Or, sorry, what does nu fin, what do the elements of nu fin look like? So nu fin was this thing here. So it's empty if m is not 1, and it's this if m is 1. So the elements are things that are sort of shaped like our Tinker Toys from before. So things like this. So the 1-to-1 map, then the 2-to-1 map, then the 3-to-1 map, and like a whole series of elements like that. And if you think about it, this category here is equivalent to the S category defined before, because what can you do with n-to-1 maps? Well, you can permute them, and you can't do anything to the base here, right? So they act exactly like S acts. And it turns out that the Monoidal product for functors for elements of nu fin is exactly equivalent to the one for symmetric sequences. So we sort of just got that by the monoid structure of finite sets here. Okay, so now I want to talk a little bit about Feynman categories very briefly. So there's a lot of different variants on operads. So props are sort of the most natural thing you would think of. So these are exactly like operads, except that it's allowed to have multiple outputs. So you can have multiple inputs and multiple outputs. For operads, we only had one output essentially, right? And then we can have cyclic operads. So these are things where there's no distinction between in and out. And then there are something called modular operads. And these are things that are, they're roughly things that have the combinatorics of Riemann surfaces. And you can keep going on and on. So that leads to a few questions here. So one question is there a common framework for all these things? Are these all just totally independent things, or is there something that allows us to talk about all these things at once? And relevant to my question, when do these structures have monoidal definitions? So let's start with the first question here. So let's recall our S category again. So roughly speaking, this abstract category S represents the notion of a symmetric sequence in the sense that all functors out of this S are symmetric sequences. They're the same data as symmetric sequences. And this is a very general pattern that you see all over the place. So we have, the general pattern is something like this. So we have an abstract category A, and we have structure preserving functors from A to C, and these are our representations. And like I said, this idea is very ubiquitous. So, for example, a group can be considered a category. So it's a category with one object. And its representation, so the functors out of that one object category are the same data as G actions, group actions of G. Another example is we can consider the category of finite injections. In that case, its representations are what are called FI modules. And another one, which is maybe not as familiar, but relevant to what I'm trying to do, is what are called Levier theories, and their representations are what are called modules in algebraic theory. It's a very common idea to have an abstract category A and some structure preserving functors, which are their representations. Okay, so is there an abstract category whose representations are operads and props? Yes. So I don't have time to get into exactly what these things are, but there is some abstract category O, whose representations are operads, and some abstract category P, whose representations are props. And you can do this for every known variation of an operad. And these things are special types of categories called Feynman categories. And also a nice fact is that algebras of these things are also Feynman categories. So we have operads and we have algebras over those operads. And those algebras can also be represented as Feynman categories. That's a nice feature of the theory. So why did I bring this up? Well, there's this basic idea in operad theory that these operad-like structures sort of organize themselves into a hierarchy. So we have algebras which are in a certain sense subordinate to operads in the sense that a particular operad, so one operad dictates a whole family of algebras. And you can continue, so there's a notion of a hyperoperad, and those do kind of the same thing, right? So you have a particular hyperoperad that dictates a whole family of operads, and so on and so forth. So there's a lot to say here, but it's really more of a rough idea than a precise statement. So one thing you can do to sort of go up the ladder is something called the plus construction. So if we have one Feynman category, we can move up the ladder by doing this plus construction. Okay. So that allows us to answer the second question. So roughly speaking, an operad-like structure has a monoid definition if its Feynman category is a plus construction of something. So every operad-like structure has a Feynman category, and I can define it as a monoid as long as it's a plus construction of something. And I can make this a little bit more precise. So precise theorem is that there's a one-to-one correspondence between bow tie monoids. So those were the monoids that I showed a few slides ago. One-to-one correspondence between those monoids and functors. Oh, sorry, bow tie monoids and C representations for Feynman categories. For Feynman category F, which is the plus construction of something. Okay. So that's it. Are there any questions?
Let's thank Michael for the talk. I'm gonna figure out how to stop recording.